Direct conditions are existence of Fourier series, existence of Fourier transform. So these are the three concepts. First one, integration of x of t should be less than infinite, or x of t is absolutely integrable. Otherwise, x of t signal should be stable signal. That's it. If the signal is stable, then only we can go with Fourier series and Fourier transform. And second and third point, even though these two signals look like a periodic signal, or it's a periodic signal only, but Fourier series cannot able to apply for these kind of signals. Yes, it has infinite number of frequency component within a fundamental time period. Okay. So unstable system, and these kind of signals, Fourier series as well as Fourier transform, we cannot apply. So remember this concept, right? So we'll start solving some problems in continuous time Fourier transform. So these are all important formulas. First one, x of t equal to del of t. Find the continuous time Fourier transform. Okay, x of t in time domain. If we find the CTFT of this signal, which is represented by capital X of j omega. So x of j omega result in the form of XOR of j omega plus j XOR of j omega. Real part plus imaginary part is available. So modulus of x of j omega, that is root of XOR of j omega square plus xi of j omega square. So if we plot omega versus modulus of x of j omega, this is called frequency spectrum. Angle of x of j omega, formula tan inverse of imaginary part divided by real part. So if we plot omega versus angle of x of j omega, then this is called as phase spectrum. Okay, so this is magnitude spectrum, this is phase spectrum. Formula for modulus of x of j omega, formula for modulus of angle of j omega. Right. X of t equal to del of t, find the CTFT. So what is the formula for continuous time Fourier transform? Integration minus infinite to infinite x of t e power minus j omega t dt. So we know that del of t is valid at t equal to 0 only. What is the signal sketch for del of t? At t equal to 0, the area under this curve is 1. Remaining all other time instant, the magnitude of the signal is 0. So minus infinite to infinite, x of tau replaced by del of t. Del of t e power minus j omega t dt. So already we have discussed in unit 1 integration related with del function, how to solve it. Okay. So del of t dot e power j omega t. This product is valid at t equal to 0 point only. We cannot apply lower limit, upper limit, and this entire product is valid exactly at t equal to 0. So your final result is del of t equal to 1 at t equal to 0. So in the rest of the term, wherever small t is there, all the t's are replaced by 0 values. Okay. So integration of del function related terms, already we discussed in unit 1 how to write the result. So del of t becomes 1 at t equal to 0. Okay, 1. So here this t is there, this t also replaced by 0. We have to check del function, del of, when it becomes 1. At what t value this del function become 1. In this example, at t equal to 0, del of 0 become 1. So this t e power j omega t, this t also replaced by 0, e power 0, 1. So if you find CT of t, Fourier transform of del of t, the result is 1. Okay, please remember this. Later we are going to use this formula, inverse Fourier transform using partial fractional method. That is simple problem. Second formula, x of t equal to e power minus at dot u of t. Find the Fourier transform and plot the magnitude and phase response. Magnitude response and phase response. The previous example also we can plot magnitude and phase response. Del of t, if we find Fourier transform, 1. Imaginary part is 0. So if we plot magnitude response, omega versus x of j omega, root of 1 square plus 0 square. There is no omega term here. So the magnitude response for this is a constant one. Okay. Imaginary part is 0. So phase response for this ft of del of t, angle of x of j omega 0 only. Because tan inverse of b by a. Tan inverse of 0 by something, tan inverse of 0, 0, 1. So this is magnitude response, omega versus modulus x of j omega. Phase response 0 for del of t. Right. Second is a standard problem. Most of the time you may expect in the semester exam, as well as for inverse Fourier transform, particularly using partial fractional method, this formula is very important. E power minus at ut. Find Fourier transform and draw the magnitude spectrum and phase spectrum of this particular set. Write the formula first. X of j omega, general formula minus infinite to infinite, x of t e power minus j omega t into dt. But e power minus at u of t, e power minus at multiplied with ut. So we know the u of t function, u of t is valid from 0 to infinite only. So if you multiply e power minus at u of t, then your signal would become like this. 0 to infinite. It's a decreasing exponential. Okay. So your integration limit now changing from 0 to infinite because the term u of t is available. So x of j omega equal to integration 0 to infinite e power minus at. U of t value 1 from 0 to infinite. As per the formula, e power minus j omega t into dt. Now solve this integration. E power minus at. So if we take common minus t outside, you will get a plus j omega into t. So e power minus at to the integration e power minus a plus j omega t divided by minus a plus j omega. Substitute the limit 0 to infinite. So what is the value now? X of j omega. X of j omega equal to e power minus infinite. Remember, e power minus infinite equal to 0. E power infinite equal to infinite. And e power 0 equal to 1. Please remember this one. So t replaced by infinite minus e power minus infinite 0. Minus of this minus plus e power t 0, e power 0 or anything power 0 is value 1. So 1 divided by a plus j omega. So remember, e power minus at ut, if we find the Fourier transform, the result is 1 divided by a plus j omega. Or if the result x of j omega is 1 divided by a plus j omega, inverse Fourier transform result is e power minus at ut. So this is second important formula in CTFT. Now Fourier transform of e power minus at u of t signals we have calculated. Next, draw the magnitude spectrum and phase spectrum. Draw the magnitude spectrum and phase spectrum. What do you mean by magnitude spectrum? How the magnitude of x of j omega distributed over the frequency omega. Omega modulus x of j omega. So we take omega value 0, 1, 2, 3, 4, 5, and omega value -1, -2, -3, and find out modulus x of j omega. Similarly, phase response or phase spectrum. How to sketch phase spectrum of a signal? Omega versus angle of x of j omega. Okay, so omega 0, 1, 2, 3, at least 5 to 6 value, positive value of omega. This side 5 to 6 value negative values of omega. Okay, and draw the line all these points. So you will get magnitude spectrum and phase spectrum. So you have to use the calculator to draw the spectrum. First make a table. What is x of j omega? This is in the form of complex number. J in this format. So modulus of x of j omega, real part square plus imaginary part square, root of a square plus b square. Angle of x of j omega, tan inverse of real part divided by imaginary part. Okay. So what is the result in this particular example? 1 divided by a plus j omega. 1 divided by a plus j omega. X of j omega, we got 1 divided by a plus j omega. Okay. For this signal, you find modulus of x of j omega for different values of omega. Angle of x of j omega for different values of omega. So first, you split this equation in the form of real part and imaginary part. So how to do it? 1 divided by a plus j omega. Multiply both numerator denominator by complex conjugate. A minus j omega divided by a minus j omega. So a minus j omega divided by a square plus omega square. Now real part is a divided by a square plus omega square. Imaginary part is minus omega divided by a square plus omega square. Okay. Now this is your xr of j omega. This part is xi of j omega. Now you got a clear idea. So root of xr square plus xi square, tan inverse of imaginary part divided by real part. Okay. So this is one way. Or in the textbook, x of j omega. So modulus x of j omega, you consider this part real part, imaginary part. Or so you can directly write modulus x of j omega for this equation. 1 divided by a plus j omega. So modulus x of j omega is equal to 1 divided by root of a square plus omega square. Okay. Or you can use the general formula with the help of this x of j omega term. So whichever is convenient for you, you can use it. Using this step, you find modulus j omega, or in the textbook, they are solving directly for 1 divided by a plus j omega. Angle of x of j omega minus tan inverse of, because 1 divided by a plus j omega term is there. So we put minus. Now substitute for omega value, find modulus j omega and also angle of j. A is a constant. You have to assume any value for A. Or in the problem, they will specify draw the magnitude spectrum, phase spectrum for A value 1 or 2, something like that. Okay. Let assume A value equal to 2. Let assume A value equal to 2. So draw a table first. Omega x of j omega, angle of x of j omega. Okay. 0, 0.5, 1, 2, 3, 4, 5. This side minus 0.5, minus 1, minus 2, minus 3, minus 4, minus 5. So like this, you draw a table. You must use the calculator. There are some standard signals available. So if you know the shape of the spectrum of a particular signal, you can directly draw the signal, no issue. But I'll explain to you how to draw the magnitude response, phase response. First, with the help of the calculator, so we have to do what is modulus x of j omega, what is angle of x of j omega. Minimum 10 points. Center point 0 and right side 5 value, left side 5 value. Okay. So assume a value 2. Substitute a equal to 0. Substitute a equal to 0. So in this equation, a0, sorry, a2 omega value 0. So 2 square 4 again root 2, you will get 1 by 2. 1 by 2 is 0.5. Omega 0, tan inverse of 0 by 0, you will get 0 degree. Substitute omega 0.5 here. Then you will get value 0.485. 0.485. Use the calculator. For 1, you will get 0.447. You will get 0.35. You get 0.27. Verify this value with the help of your calculator. 4.22. 5.185. For the negative value, minus 0.5, again you will get same value, 0.485, because 1 divided by root of a square plus b square. So 0.5 minus 0.5 will get same magnitude. For this example, 0.447, 0.35, 0.27, 0.22, 0.185. Okay. For angle calculation, omega 0, you'll get 0. If you substitute omega 0.5, a equal to 2, you'll get minus 14 degree. That's minus 14. Minus 26.5. Minus 45. Okay. minus 56.3, minus 63.43 for 5 minus 68. Negative value of omega will get reversal. You will get 14, 26.5, 45, 56.3, 63.43, 68. Okay, so verify this result with the help of your calculator. Now the table is ready. Now plot your magnitude response, phase response. Modulus x of j omega, x-axis omega. So 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, minus 5, and so on up to infinite. Okay, 0.5. This is 0.5. Then 0.48 by 0.447. So this side minus 0.5 minus 48. So you will get the signal like this. Okay, this will be decreasing up to infinite. If you mark the amplitude of x of j omega for each and every values of omega, so your magnitude spectrum for this particular signal go like this. Okay. Like this. This is 0.5. 1, 2, 3, 4, 5, 6, and so on up to infinite. Minus 1, minus 2, minus 3, minus 4, up to infinite. Okay. Phase response. Angle of x of j omega versus omega. 0, 1, 2, 3, 4, 5, and so on. Minus 1, minus 2, minus 3, minus 4, minus 5, and so on. Okay. So omega 0, your angle x of j omega 0. Okay, 0. 0.5 minus 14. 1 minus 26.5. 2 minus 45. 3 minus negative value of omega at minus 0.5, 14. Minus 1, 26.5. So if you mark the point and connect all the magnitude value, then you will get the graph like this. Magnitude response. Okay. Please remember. So this is standard signal. Once you remember this, the shape of the magnitude response and phase response for this signal, after finding x of j omega, directly you plot the spectrum. Suppose if you are not getting time to calculate modulus x of j omega, angle of x of j omega in the examinations. The phase response will go like this. is the center point. So do you understand this problem? Because whenever I start the spectrum diagram, the student have some doubts. They'll have some doubt because new concept for you suddenly. In exponential Fourier series, we have drawn the magnitude spectrum, phase spectrum for only one problem, k versus AK. There, okay. Even though the signal is continuous, but spectrum we have drawn in the discrete wave only, exponential Fourier series. Okay. In continuous time Fourier transform, your spectrum, magnitude spectrum, both and the phase spectrum, both are in continuous. Omega versus x of j omega. Omega versus angle of x of j omega. So after finding your x of j omega, calculate this magnitude spectrum, phase spectrum with this help of this formula. And draw the diagram clearly. Shall we move to next topic? Next problem now. L45. Are you there? Lateral number 45 is there or not? L50. Lateral number, roll number 50. Can you respond me?
Sir,
Are you listening the class? Where are you?
sir, listening.
So next problem, x of t equal to e power minus modulus t. So first one del t, second one e power minus at ut. Third one x of t equal to e power minus modulus t. Now how to solve this problem? Find continuous time Fourier transform of this particular signal. No, first rewrite this given problem. E power minus modulus t. Modulus t, okay? E power minus. This modulus t becomes plus t. For t is greater than or equal to 0. This modulus t becomes minus t. So minus into minus plus, you'll get e power plus t. For t is less than 0. Right? T greater than or equal to 0. This modulus t equal to plus t. T less than 0, modulus t becomes minus t. So one more here, minus is there, minus into minus plus. First step, rewrite this and apply the continuous time Fourier transform formula and solve it. X of j omega equal to integration minus infinite to infinite x of t e power minus j omega t to dt. So we have to solve this problem in two steps. One is 0 to infinite. This one. What is the x of function? E power minus t. The e power minus j omega t into dt. Plus integration minus infinite to 0. This function. So e power t as per the formula e power minus j omega t into dt. Solve it. Take e power minus t outside and do the integration, substitute the limit. E power minus t, if you take outside, you will get 1 plus j omega dt plus minus infinite to 0 e power minus t, take outside. So minus 1 this term 1 plus j omega. Here it is 1 minus j omega. Sorry. Minus infinite to 0. Okay. Right. So we'll solve this problem. 0 to infinite e power, if you take minus t outside, you'll get 1 plus j omega. That is correct. So second term, integration minus infinite to 0, let me transform into integration 0 to infinite. Let replacing all t by minus t. Then interchange your integration limit first and then solve for x of j omega. So 0 to infinite e power minus t dot e power minus j omega t dot dt plus I want to change the integration limit or replace t by minus t. The second step. So integration 0 to infinite, I'll get e power minus t into e power j omega t into dt. Okay. Please remember, to solve this e power minus modulus t problem, after substitution of the integration limit, it's better to interchange your integration limit here itself. Now 0 to infinite e power minus t, you'll get 1 plus j omega t dot dt. Here 0 to infinite e power minus t, 1 minus j omega t into dt. So e power minus 1 plus j omega t divided by minus of 1 plus j omega. Plus e power minus of 1 minus j omega t divided by minus of 1 minus j omega. Substitute the limit now. T replaced by infinite minus e power minus infinite. E power minus infinite 0. Minus of minus plus e power 0 1. 1 divided by 1 plus j omega. Here e power minus infinite 0. Minus of minus plus e power 0 1. So 1 divided by 1 minus j omega. 1 divided by 1 plus j omega plus 1 divided by 1 minus j omega. So this is the result for e power minus modulus t. And please remember, in the second step, replace your integration minus infinite to 0 to 0 to infinite. Otherwise, you will get infinite result. If it is possible, further reduce this step. 1 times of 1 minus j omega plus 1 times of 1 plus j omega. Just cross multiply. So 1 plus omega square. 1 plus j omega multiplied with 1 minus j omega. A plus b, a minus b. The formula a square plus b square. So j value, j square minus 1. This minus will be cancelled. So the result is 2 divided by 1 plus omega square. Okay. So e power minus modulus t. The Fourier transform result. 2 divided by 1 plus omega square. Okay. So if we want to plot the magnitude response and phase response for different values of omega, find out x of j omega. So in this example, imaginary part is not there. 2 divided by 1 plus omega square. This is real part. Plus imaginary part is 0. So phase response 0 for all the values of omega. You can draw the magnitude response for different values of omega. Let's complete magnitude response for this x of j omega. Omega modulus of x of j omega. Okay. So this part, real part, x or x imaginary part is 0. Okay. So omega equal to 0. Omega substitute 0. Root of 2 square. You'll get 2 1. Omega value 1, 2, 3, 4, 5, and so on. Minus 1, minus 2, minus 3, minus 4, minus 5. Substitute omega value 1. 1 plus 1, 2. 2 by 2, 1. Root of 1, you will get 1. Substitute 2 value. Omega 2. 2 square, 4. 4 plus 1, 5. So root of 2 by 5. So you will get the signal. Okay. Omega versus modulus x of j omega. The spectrum will look like this. Imaginary part is 0. So angle of j omega equal to tan inverse of b by a. Tan inverse of 0 by this 2 divided by 1 plus pi square available. Tan inverse of 0 is 0 1. So for this particular signal, for all the values of omega, it's a continuous one, not discrete. Okay, please remember. Your angle value is 0 1.